just seen this in my classroom. Now, as you'll be aware, the penalty for seeing that in a physics classroom, well, it's death. It's death. And, you know, most people might just execute this balloon with one nail, but to convey just how mad I am at this balloon, I'm going to use 100 nails. Any last words? No, because you're a balloon. Okay, here we go. Okay, that's awkward. That's awkward. The reason it's awkward is because I'm not actually taking into account surface pressure. Surface pressure is the amount of force exerted per unit of area. If I want to execute this balloon, I'm going to need to exert enough pressure on this surface to split the rubber and burst the balloon. And there are two ways I can increase surface pressure. One is by just increasing the amount of force I apply to the balloon, which I think we'll agree nobody could exert as much force as I just did. But the second thing I could do is change the area over which I apply that force. I applied that force over quite a big surface area. So I've spread the force out over a large area, which means the surface pressure is actually quite low. If I concentrate my force over a small area, just one pin, this happens. Serves you right. I should also point out I did find this in my classroom. Ignore the creepy face. This is my new best friend. Fist bump. And what he's going to do is he's going to demonstrate to you gas pressure. What gas pressure is. So gas pressure is made because inside this balloon there is air, and that's made of particles. And the particles are zipping about inside the balloon, colliding with the inside wall of the balloon. And every time they do that, they exert a little bit of force. The more often they do that, and the harder they do that, the more pressure there is inside this balloon. How could I increase the pressure on this balloon? Well, there are two things I could do. One very simple thing I could do is to decrease the volume by squeezing it. I'm now giving the particles a bit less space to travel from one wall to the next, and therefore they end up colliding more often. This is the relationship between the pressure and volume, and it's called Boyle's law. I can show you how it works on the board as well. So here are the air particles inside the balloon. And if I decrease the volume, you should see that the pressure dial over here increases because the particles are hitting the side of the container more often because they've got less space. A second thing I could do is I could change the temperature of the gas. Okay? Oh, sorry. We're still friends, it's okay. Now if I change the temperature of the gas, then the particles themselves are going to start moving more quickly, and each one will exert more force on the container walls. So we'll do that, and you should find that as the temperature rises, so does the pressure. This is the Gay-Lussac law. Eventually the pressure inside here will become so great that the lid can't contain it, and the particles literally blow the lid off. I can show you a practical example of how that works right here. So what I'm about to show you might seem like magic, and some would forgive you for thinking so. I wouldn't. I would think you were an idiot. But let's have a look at it anyway. So inside here, you probably can't see, but there is a small amount of alcohol in liquid form. And I'm going to increase the pressure on this alcohol simply by pumping air into it. Now by doing that, by increasing the pressure, I'm going to increase the temperature, as you saw on that simulation. And what that does is it means that the alcohol will actually start to vaporize. It'll turn into a gas, and the gas will spread out throughout the bottle. But that's not the cool part. The cool part comes when I reduce the pressure. I'm going to reduce the pressure very suddenly by yanking out this stopper at this end of the bottle. And that huge drop in pressure is going to mean a huge drop in temperature. What you should see is that the vapor alcohol will turn into a liquid, and you will see that as a cloud, like a cloud of condensation. This is effectively a cloud in a bottle. Pretty neat. And this actually feels a little bit colder. You're just going to kind of have to take my word for that. Okay. I could increase the pressure and temperature again, and the cloud would vanish. As you can see. And so the third relationship between gases is the link between volume and temperature. So, it's okay, we're still buddies. If I was to decrease the temperature of the gas inside this balloon, then the particles would hit the side of the balloon less hard and less often, and so the volume of the balloon would shrink. In fact, keep decreasing the temperature of this gas, and eventually you'd reach 0 Kelvin, or minus 273 degrees. That's called absolute zero, and it's the coldest temperature possible. At that point, the particles inside the balloon stop moving altogether, and the volume of the balloon would shrink down to almost nothing, just the volume of the particles themselves. Back to you in the classroom. I could show you this by putting this in a fridge or freezer, but and you might think that I'm not doing that because I can't be bothered, but the real reason is that I want you to do it. That's what I want you to do it at home. Stick this in a freezer and see what happens after you leave it for a couple of hours. It should get smaller, and that relationship between volume and temperature is called Charles' law. Oh, sorry, no, I'm really not a good friend. These three gas properties, pressure, volume and temperature, are linked by the general gas equation. P1 V1 over T1 equals P2 V2 over T2. And actually, pressure, volume and temperature all tend to change at the same time. Off camera, what I'm doing is I'm heating some water inside an aluminium can. And I'm going to try and demonstrate that all these three things change at the same time. So the water inside here is going to be turning into steam. This is a heater. And so inside the cola can, you're going to have very fast-moving steam particles hitting the side of the can. But then what I'm going to do is I'm going to flip it upside down in a cold beaker of water. So what's going to change? Well, obviously the temperature is going to go down, right? But if the temperature goes down, then the particles are not moving as quickly, and so the pressure is going to go down as well, right? And if the pressure is going down, well, normally air would just flood back into the can, but we're not letting it do that because the opening is under the water. So what happens is the pressure from the air in the room will crush the can from the outside. It'll be bigger than the pressure on the inside. And so the volume of the can changes too. Okay, I think my can's just about ready. So I'm now going to demonstrate this to you. Here's my beaker of water. Here's my can. Boom. Physics is true. Yeah. Okay, one more parting piece of information. I hope you learned a lot on that. But when you're in the exam, please take heed of this advice. You have been warned.